We are pleased to have Lori Sanford as our presenter. Lori Sanford is an HPLC application scientist with Agilent Technologies in Wooddale, Illinois. Lori has been working at Agilent in supporting HPLC instrumentation since 2010, including 2 years with Varian working as an HPLC specialist. Prior to Agilent, she was the Global Technology Manager for Prep and Process Chromatography at W.R. Grace/Altec. Her career started at GD Cyril Pfizer in 1998 as a chromatography specialist in the Prep and Process Chromatography group, supporting both medicinal and process separations. Lori attended Florida State University, where she received her degree in chemistry. When not tinkering in the lab, Lori enjoys time at home with her 2 teenage boys, shuttling from hockey rink to the lacrosse field, enjoying concerts, or planning her next scuba adventure. All right, it gives me great pleasure to turn today's event over to Lori Sanford. Lori, please go ahead.
Thank you so much. Happy 2021, everyone. Happy New Year. Thank you for joining us today for our webinar. Today I'm going to present some information on our analytical to preparative chromatography, really with a focus on preps for smaller scale. We'll go into some details about that, so let's go ahead and dive in. Before I get started, I wanted to let you know that if you have questions during the presentation, feel free to put those in our Q&A, and Patrick or I will get to those questions during the presentation, and then hopefully we'll have some time, if I don't go into too much detail on the slides, to answer some questions afterwards. So thank you again. There we go. So today I'm going to focus on our analytical scale, but I wanted to make sure and show you about our new prep chromatography product line in case you haven't seen these products. They're really great. What we've done is revamped our preparative chromatography products in the past couple of years to bring the best from our Varian acquisition prep products and the Agilent prep product line into a new cohesive product line that really spans everything from analytical to benchtop process chromatography. I'm going to go into a little detail on these instruments before I talk more about the analytical portion. On the left, you'll see that we have our pumps, and these are our higher flow pumps, not the analytical pumps. This is our 1290 prep binary pump, and then our 1260 prep binary pump. These span our flow rates from anywhere 1 to 50 mils a minute on the smaller pump heads, and then anywhere up to 200 mils per minute if you add the 1290 with the 200 mil per minute heads. These are really great pumps. It's a small format for the amount of power you get with these, and it's a binary format, so you don't need to do any sparging of your system. As we move into ways to inject your sample, we have, of course, a more manual way with a manual injector with lots of different options for loop sizes. And then we have our vial sampler, which is upgraded to a larger format for larger injections, and this is our vial sampler version. And then we have our newest module, which we're very proud of, which is our combination open bed fraction collector combined with an auto sampler. So this can do all of your liquid handling needs to get your sample injected into your system, whether it's an analytical or larger volume sample. We have both analytical and prep loops on here. And then after you separate your sample, you can collect into this open format, which is just like our open bed fraction collector. And you can have different types of tubes. I'll go into some more detail later about this as well. But one of the great things you can do here is homogenize your fractions and re-inject aliquots of those fractions back onto your system, either for further separation or for reanalysis of these fractions after they've been run. So it pretty much does everything from start of the run and then finishes up at the end of the run, and it has a small footprint as well compared to having 2 modules. Here's some extra accessories. We have our new flow modulator, which is an active splitter. I'll talk about that a little bit more later. And then some column holders, organizers, valve holders, and these have built-in leak sensors, which are really nice for unattended operation. A variety of detectors, pretty much everything you're used to, all the way from standard UV detectors, ELSDs, adding on mass spec. These can all be done at a later date, easy with CAN cable connections, just like you have in an analytical system. If your application needs change, it's easy to swap things out or add them to your system. And I'll go into some detail about how you can utilize these different detectors for some maybe orthogonal detection. And then finally, we have our fraction collectors. We have a wide variety of these to really span all different types of fraction collection. Here's the open bed format, which I mentioned in the combination module, but this is just for fraction collection. This has a very large format. You can manipulate your fractions while the system's running. Here we also have a smaller format that's a closed fraction collector. This is our 1260, and this can have a variety of different collection vessels, mostly tube sizes. And then we even have a valve-based collector, which is really simple, and this can be used either to just have tubing from different positions up to 11 different positions, where you can collect into maybe a dewar or a flask, depending on what size column you're running. But you can also put this valve-based collector after a fraction collector to use it as a recovery in case you have one of those oops moments where maybe you missed a sample. You can have each of these locations going into a clean vessel, and that way if your sample or something you needed goes to waste, you have a clean vessel for each injection up to 11 positions. So that's a really nice add-on to a system. But today what we're going to do is really focus on analytical. So I'm going to talk to you a little bit about the differences between just standard analytical HPLC and preparative HPLC. So what's the difference? I hear a lot of different questions or definitions. People are like, oh, well, I'm not flowing at 100 mils a minute. Well, that doesn't define prep. What really defines prep is that rather than going from our detector to waste, we have the option to go and collect fractions. So whether you're flowing at 1 mil a minute or 200 mils a minute, it's all prep chromatography if you're collecting fractions. So you're always going to have a pump, some way to inject your sample, whether it's a manual injector or auto sampler. You're going to have some means of separation, a column. You need to detect those peaks, see where things are going, and then say, you know, I don't want it, it can go to waste, or I'm going to collect a fraction, whether it's by time or peak or what have you. This is a typical drug discovery example. This is probably our most common application is this purification work cycle in pharma. So a lot of times, you know, we start in maybe a med chem zone where we're analyzing crude product. We get some information, and then we say, okay, here's a peak that we want to collect. So we do some method development, get a separation, and this may be analytical scouting, target confirmation, and then scale up from that analytical column to our purification column. Now, if you're doing analytical prep, that column may be the same size or it may be slightly larger. But what we're going to do is collect the amount that's needed with the needed purity, and then we need to determine the purity of these fractions we collected. So we analyze these, we may pool them, and then after we pool the fractions or combine what we want, we then could determine the purity of that as well. And then wherever it goes next, it may go into a tox study, it may go into the next step in your chemistry, what have you. I wanted to break down the analytical portion of our prep portfolio and how you might determine what system would best meet your needs. So the parts that you can't see very well are grayed out because these are our larger scale systems. When we're talking about analytical, usually we're going to be in this 0.01 to 10 mil a minute range. This is actually a pretty wide range for an analytical system. You'll only reach this 5 to 10 mil per minute with a quaternary pump and at a 200 bar pressure or lower. What I typically see in the lab, most people are running these analytical systems below 100 bar. So going over this 200 bars is somewhat uncommon. There are ways you can also reduce the pressure in your system with larger tubing or larger particle sizes in your columns to get this lower pressure so you can achieve this higher flow rate. But if you're within this 0.01 to 10 milliminute, you can easily go into one of these analytical scale systems, right? And then you can see how this is broken down into how much can I run on an analytical system. What we're typically talking about is this microgram to milligram range, right? Because we can support the columns below at these flow rates. So to have a good linear flow rate or an ideal linear flow for these columns, we want to stick with anywhere, you could absolutely run a column smaller than 4.6 ID. You could run a 2.1 or what have you. So let's say a 2.1 millimeter ID all the way up to a 10 millimeter could be run very comfortably on an analytical system. And these are the typical flow rates for these columns, which are also broken down into this chart. So I just put a box around the typical analytical sizes. And then what you can see also for these analytical columns, not only the ideal linear velocity or flow rate going through these columns, but the purification range of your compound. So anywhere in this up to maybe 10, 50, even 100 milligram range on a column, depending on how good a separation you have, your resolution, the order of your peaks. So you want to make sure that when you're looking at these guides, you go, okay, I need to have a separation that kind of works if I want to be on the upper edge of the limits for the columns and for the flow rates, right? So let's talk about the system a little bit more. In the analytical systems, what we have I'll start at the left, we have this 1220. So this is what I like to call kind of like system in a box. This is a great system for somebody doing like QC or very like standard applications. It's not a modular system, but it does have almost the same components that you would see in a 1260. But there's not as much flexibility or options for the system. So if you don't need to change things very often, this is a good and economical way to get into an HPLC. But really when we're seeing purification added to an analytical system, usually what we're seeing is this 1260 range. And 1260 is a standard LC. If you have our older 1200s, 1100s even, these are that same product line, just more bells and whistles, modernized, things go faster. We have a lot of neat features that have been added in the past few years that bring this up to this Infinity 2 line, okay? So we have binary pumps, we have quaternary pumps, and then we even have a bio-focus pump, our bio-inert. Sorry, I keep clicking on this and advancing by accident. So we have bio-inert options, but you can also add purification to a UHPLC system, so the 1290 line as well, if you're already doing UHPLC. So that would be the 1300 bar range. And if you haven't heard, it's so new, I haven't even added a slide for this yet, but we also have a new bio-inert UHPLC pump. So if you are in the market for something that's bio-inert, a lot of people in the protein field, feel free to contact one of us and we'd be happy to talk to you about the new system. But you can basically take any of these pumps and you can add a fraction collector to the ends, and then all of a sudden you have a purification system. So let's talk a little bit more about the pump that I see most frequently, which is this 1260 quat pump. And this is a pump that you can see can go up to 10 mils a minute at up to 200 bar. Or if you're under this 5 mil a minute, you can go up to 600 bar even, which is a pretty high pressure. So you can absolutely do prep at a high pressure with a very small particle size if that's what you're using. You may not get that higher flow rate, but that's okay. You could even use a porous shell column, and that would greatly reduce your pressure and allow you to go up into this higher range. Just remember, when you're using columns that are superficially porous, typically they don't have the loading capacity that a fully porous column would have. But what I'm seeing is most people aren't loading in an analytical range to the point where they need that fully porous material anyways. I didn't mention this at the beginning of the presentation, but you guys have the option to opt in and get all of these slides. There's many slides that I've hidden just for the sake of time. So if you see details in here, things like the specifications, or later you'll see some scale-up equations, you'll have access to all of those, and I may just skim over them and not go into a large amount of detail for the sake of time. These are the different auto samplers that we typically would see on an analytical system for preps. We have anywhere from our UHPLC version, which can handle that 1300 bar, also available in the bioinert, but typically what we'll see is the 1260. And the vial sampler is the most simplistic version, and as its name suggests, it will handle vials, but vials with different volumes. You can have 6 ml vials, 2 ml vials. If you have higher throughput needs or you want some more flexibility for different containers, the multi-sampler is the way to go. So you can have so many samples in here. This is a hotel-style auto-sampler. So you have many different drawer options. You can have depot plates, well plates, 2 ml vials, and you can extend injection in this as well. All of these auto samplers now inject in a fraction of the time that it used to take to inject on our older auto samplers before our Infinity 2 line. So if you're looking to upgrade one component, sometimes upgrading the auto sampler in your system can really improve your throughput rather than waiting for a very long injection time that you might have had with, say, an 1100 auto sampler. This is just a little more information on the vial sampler, so you can see the format for the drawers. You can have the old style drawers, what we call a classic, with 100 vials in it, but the standard format is you can have 2 of these 66 vials. You can also have the 6 ml vials or a combination of the 2, and this can have an internal column compartment, which I'll show you a picture of in a few minutes. This is the hotel-style auto sampler, which is a multi-sampler, and you can tell right away that you have much more flexibility, and you can hold many more samples. Some people like to organize the trays and have one tray for 2 ml vials, one for well plates, etc. Most people doing prep like to have the option of injecting from a larger format. So you might format one of the drawers for larger volumes than the other drawers. But whatever auto sampler you get, you're still going to have our flow-through injection principle, which is very unique to Agilent. This isn't anything new, actually. We've had this for quite a long time. And what this does is it has an extra valve in the auto sampler itself, and this allows you to do flow-through injection. So when you inject your sample, of course, you can't flow through the needle if you see the diagram here. Our needle will either move to the vial or the vial will move to the needle, depending on the type of auto sampler. But this valve will switch from flowing through this pathway, through the needle, while we're picking up our sample. But once that sample goes back to the needle seat and becomes injected, this valve then becomes another flow-through style as it switches, flows through our sample loop, through the needle seat, injecting that sample in a nice discrete plug, which if you have a large volume, you definitely want to squeeze that plug and keep it as discrete as possible so you don't end up with any band spreading as you're trying to do your separation. But one of the best features of this is after you've injected your sample, you're still flowing through that needle, which eliminates any carryover on the inside of your needle. These auto samplers also have an exterior wash. You have a lot of different options. You can do some liquid handling. You can do pre-column injection, different things like that with these auto samplers, which I see quite frequently in the analytical range. Another thing we have to talk about is column heating. So for those of you who are not heating your analytical columns, you may see some irregularity or inconsistency from injection to injection. So even if you're just running at room temperature, it's nice to make sure you're regulating your temperature column, the temperature of your column for each run. So the system on the bottom is that integrated column compartment I talked about on this vial sampler. You can get a vial sampler without this column compartment and add an MCT or external column compartment if you want some extra capability. As you can see here on this external column compartment, you can add a valve to do automated column switching, which is really nice if you're doing method development. This is a new design, so it's much more ergonomic. You can see that the column preheaters are set up behind the columns now. They're much less fragile. So you're heating the solvent prior to it entering the column, and you're heating your column. This eliminates any thermal gradients across your column. In other words, you'll keep your band together. There'll be less band spreading, because if you just heat the outside of your column, often just due to thermodynamics, you'll see the outside of the column, the things closest to the column, moving more quickly, and that leads to band spreading. And you can have, different retention times based on temperature. So it's really good to make sure that you have that door closed and you regulate your column temperature as well. There's lots of things you can add to the systems as far as consumables now. This is my favorite. If you're switching columns frequently, using these quick connect fittings is amazing. You don't need a tool. They're pressure rated up to 1300 bar. They have a little spring inside which pushes the fitting all the way to the end of the inside of the column. So no matter which manufacturer's column you're using, you don't end up with any extra mixing space or any mixing volume in that column. It's a really nice feature, and I always recommend you have these on the inlet to your columns on your system. We move on to detection, and it's really the same detection you expected from Agilent. The most common detectors I see for prep are always UV. People also add other detectors. It's very simple to do, but I'll focus mostly on UV since it really, I'd say 90% of our prep customers run UV detection. You can run this with other detectors. There are many different types. The most common detection for larger scale prep is the variable wavelength. But on analytical prep, since what I see most commonly are people doing multiple techniques, not just preparative, I often see diode array on the system. So this diode array at the bottom, the wide range diode array, is what I would recommend for most people doing preparative chromatography on an analytical system. It has a more rugged flow cell in it, so it's less delicate than the high sensitivity flow cell we have on this other system. You can use the high sensitivity flow cell with prep, but since you have a valve after the detector when you're doing your fraction collection, I recommend anyone using a fragile flow cell have a pressure relief valve on there just to protect that flow cell. But on the wide range one, you also get the ability to have a second lamp on there so you can see the visible range. It's less likely to, it has a higher pressure rating on the flow cell. You can get an even higher one if you go at much higher flow rates. So it works quite nicely. Anytime you have a valve after the detector, having that pressure relief valve is a good idea. So if you add mass spec, that's also a good idea on that sensitivity flow cell. So here's just some more specifications on the diode array. This is just for your reference. The data acquisition on this goes up to 120 versus, I believe, I think it's 180 on the other model. It may be higher. Patrick can correct me if I'm wrong. Most people doing even non-prep, regular analytical HPLC don't need over 80 hertz. 80 hertz is quite a stretch. So the ability to go to 120 hertz is really forward compatibility should your needs change. So that's 120 hertz is 120 data points per second. That's a pretty sharp and small peak for you to need to analyze at that data rate. Here are the fraction collectors that are typically recommended on an analytical system. So these are our two analytical fraction collectors. You can see the other ones I mentioned grayed out here, but these are recommended up to 10 mils a minute. We have a bioinert version and our standard version. These are both closed format. You cannot open the door while they're running, and this protects you from any fumes escaping from the fraction collector. 240 hertz. I knew I was underestimating that. Thanks, Patrick. And then you can see for well states, we can go up to 384 fractions on these systems. You can daisy chain these fraction collectors as well. So if you want to add additional fraction collectors, it's very easy. They're stackable. It has a very small footprint. And this is typically sufficient for most analytical injections. You can, of course, go up to the larger format fraction collector if you wanted to do the open bed. So once I talk about fraction collectors, I always have to talk about the fraction delay sensor, because I think this is one of the things that's really a differentiator with Agilent. It's something we do, I think, better than anyone, and it's something we've done for quite a long time. So talk about the fraction delay sensor, we need to talk about what is fraction delay. So when you have a fraction collector added to your system, whether it's analytical or process, you will have a time or a volume where you're seeing your peak being detected in whatever detector it is, UV, mass spec, what have you, but that peak is not yet, hasn't traveled to your fraction collector. So you don't want to open your diverter valve and start collection when you first see the peak. You want to make sure and calibrate it so that it knows that volume or time it will take to travel to that diverter valve so that you have collected exactly what you want to collect with the purity you want. Most people have history doing this with a stopwatch and some dye and relying on their vision and seeing this colored dye move through the tubing and going, okay, at this flow rate, it looks like it starts at this point. But that's kind of a hit or miss. It's laborious to change frequently. So what Agilent has done is has added a detector or a sensor near the diverter valve in the fraction collector. And this is in all of our fraction collectors so that you can do this in an automated fashion. And then once you set this and calibrate it, it's automatically set into your system so that for UV detection, whenever you change your flow rate, it knows that it will change that delay based on volume, not on time. So this is how you would do this in the software. It's so simple. All of the systems come with this calibration die. And if you have a mass spec, we also add an ionizable component to the calibration mixture. You just walk this through in either ChemStation or Open Lab, or you can also do this in Lab Advisor, which is how historically this was done. And the way I do it is I usually do 3 injections, and I take a look at them. If they're all similar, I can either average those 3 distances, and what you'll see is the chromatogram just like this is. So you'll see your UV peak, and then you'll see your peak as it hits your fraction collector sensor. The system will tell you what that volume is. You don't even need to calculate it. So you could do some weird flow rate 1.247, and it would know that volume automatically. And then all you do is say, yes, accept this, and it becomes part of your system parameters and stored with the firmware of the system. So it's really easy to do. When do you need to do this? Well, you do it when you first set up your system. And then if any of your parameters change on your system, like if you change the tubing and you might have a different volume, or you move your system, you might want to check it just to make sure it's the same. And you can check it at any time. You don't have to accept the data if it's the same or if you don't need to do any changes. So a really nice feature, and it can give you the confidence you need to know that you are purifying your sample exactly the way you want to purify it. So we'll talk a little bit more about detection. You can really use any of these detectors for peak detection, right? So say you have a variety of different samples, which often happens in the analytical realm. You may have some that have chromophores. Great, you can use UV detection. But what if you're running I don't know, fats or something one day, and you can't see any of this on your UV detector. Maybe you have an ELSD. You add the ELSD to the system. You can use that to say, okay, I want to collect based on my ELSD signal. Or maybe you don't want to collect a whole bunch of fractions, but you know the mass of your peak of interest. Maybe you go, today I'm just going to collect based on mass. So whatever you use to direct your fractions, you absolutely can do that. Maybe you don't want to depend on a detector because you've never injected this sample before and you don't know what it's going to look like. So maybe you just collect based on time, which here's a view of the software itself, the screen in ChemStation. When you add a fraction collector to your system, the only difference in the software view is the addition of the module, which is the fraction collector, and then you can see the blow up of this screen when you're setting up your parameters. Very simple, you walk through it, enable fraction collection. You have the choice to select which detector you want to use to guide your fractions if you're going to use a detector. And then maybe you're going to use one of the signals. So you might use your A signal, B signal. So for instance, if you have a multiple wavelength detector, you may use your B signal, which is 180 or 254, rather than what you have. And you can change these functions over time. You have a lot of flexibility here. You can have this based on threshold or height of your signal. You can have it based on upslope, downslope. Upper threshold is nice. You can cut off collection at an upper threshold so that if you exceed the range of your detector and things get kind of rocky, I don't know if you've ever seen that. I call it the Bart Simpson hair top of your chromatogram. You don't want to collect a million fractions because it's moving up and down, so you can limit that upper threshold as well. So lots of flexibility here. You can have different trigger combinations. You can say, I want to collect if you see any of my parameters that meets these guidelines, I want you to start collection. Or you can make it more limiting. I want everything listed to be satisfied before you start collection. That's pretty strict, right? I've seen that as a gotcha many times. You can also say, you know what, I don't want to collect anything this time, or I want to turn off collection for a few minutes. You have all of these pull downs, so it's very user-friendly. You just go in here and select, okay, today I want to do time-based, or now I want to do peak-based. And then maybe after 5 minutes, I'm going to turn off collection because I don't need any of those late eluting peaks. So lots of things you can do here. A really nice feature, which I didn't include in my slides, is this fraction preview where you can look at data you've previously run, and you can use that, click on that data, you can click on your data in fraction preview, and it will set these parameters for you. And you can see how you would have collected had you set those parameters that way and with your previously collected data. So really nice setup for the fraction collector. When you're collecting fractions, if you're just starting out into this, there are a few things to think about, like, for instance, what is most important in your analysis? And this is our purification triangle. So you have to make some compromises depending on your separation. So if you do an analytical run and you don't get the best resolution between your peaks, you may have to compromise your purity over your yield. For instance, in these peaks, for number one, we have some overlap here. But if you want to collect everything, if this is a very precious sample, you're going to collect some of your material that may not have separated from the early eluting peak. Or maybe you want high purity. So then you can change this and you can say, okay, I only want to collect the apex of my peak for high purity. So you may have to compromise yield over throughput, et cetera, depending on the goals for your separation. This is just an example of how you might collect peaks by UV. So you might set your UV to, for instance, threshold, and your threshold may be 50, or I guess it looks like much lower, maybe 10. So everything we collect here is satisfied by that requirement, so we collect 3 peaks. But how do we know which one of these peaks are our peak of interest? Sometimes you can guesstimate this. Typically, maybe your peak comes out first, but more than likely you're going to have to do some reanalysis of your fractions afterwards. One way that you can avoid this can be adding an orthogonal technique like mass spec to your system. There are two main ways that I see customers using mass spec on an analytical purification system. One is exactly as I mentioned, where you may use the mass spec to guide a specific mass or collect a fraction based on that mass so that you're only collecting your peak of interest or the peaks that you care about. You can dial into multiple masses as well, and that would be your M over Z for this. Or what some people do is maybe you don't have a lot of information about your compound yet. Maybe you're in an early stage in your med chem department. You collect based on time, or you collect based on UV, and then you also collect mass spec information on your run. And then you can have the mass of the components or maybe see multiple masses, and that might give you more information as to what that compound is. So adding other or orthogonal detectors to your system can definitely increase the amount of information. And as you can see in this example, you can reduce the amount of fractions you collect as well by adding something like a mass spec. So in the A component on the top, we're collecting by UV, so we collect multiple fractions because we see multiple peaks on UV. But when we add the mass spec and we say, hey, we only want to collect a specific mass, it looks for that and maybe the UV, depending on how you set up those parameters I mentioned previously. And now you know that you have one fraction and you don't have to deal with as many fractions, and you may not need to do that extra confirmation step. Remember, if you add a mass spec to your system, that you're going to need to do some splitting. Some people use passive splitting. What I recommend is to add an active splitter. We have a brand new splitter. It's wonderful. It's called the Flow Modulator. You can control it completely in the software. So if you need to change your split ratio for multiple reasons, you can do that on the fly. It's quiet. It's robust. If, for instance, you need to add an extra modifier after your pump. For instance, some people use modifiers that are not mass spec friendly for their separation, but maybe you split off most of that and then you add a mass spec friendly modifier at your mass spec into the active splitter. You can absolutely do that as well. If you need more sensitivity, you can dial up that split ratio and send more to your mass spec. You want to remember that mass specs are destructive, so you have to split and send what you want to collect to your fraction collector. Some people flowing at 10 mils a minute, you definitely don't want to go into an electrospray at 10 mils a minute. You're going to drown your source. You'll get much better sensitivity at a much lower flow rate. So that split is useful when you're trying to improve your sensitivity as well. So lots of reasons to add that active splitter on there. Mass-based fraction collector, here's another example where we're just triggering the top part of the chromatogram is our UV signal using a diode array, where if we only collected on UV, we would collect all 4 of these peaks. But you can see we dialed in our compound mass, so the target mass is 278.2. We added the +1 for the hydrogen adduct, and then we also added our sodium adduct. So we were able to collect on the mass of this target ion in our peak, and you can see that the mass spec signal is the lower signal here. So it adds a lot of extra confirmation and also selectivity to your sample. Okay, so you may be going, well, where do I start in this? I don't know what to do. I'm brand new. The first thing I recommend is think about what you're separating, okay? So we might know a little bit. We have a small molecule. It works well on a C18 column. And then I want to think about how I do some method development and scale up. Go to one of our guides. We have an amazing primer. It's so good. It's available electronically. The last page in my presentation has a link for that you guys will get as well. We've got all kinds of column guides. You might want to think about what solvents you're using. Maybe you're going to use some of our special method development software. Whatever you use, there's so many tools available to you, and if you are having trouble navigating this, absolutely you can contact us to get some more assistance with this. So a lot of these solutions are directly provided by Agilent. So whether it's different columns with different chemistries that'll help you separate better, or maybe as you scale up, you want larger particle sizes or non-fully porous materials, things like that, or maybe those great fittings that you can switch columns. But you can also look at things like software add-ons. The Method Scouting Wizard is one of my favorites. I love this software. We'll do separate webinars on this, or you can get extra information from us, but it's a great way to screen different methods, different columns, different solvents. I'll talk a little bit more about that. And then, of course, our regular OpenLab or ChemStation software are excellent tools. We've got a lot of great help sessions and tutorials in those as well, and then great ways to do some reporting for your analysis. So I did want to just quickly touch on the method scouting because it is so great for method development. It's just an add-on, as you see here, to ChemStation. And it adds right onto this top bar. You just say, okay, I want to start a new campaign and do some method scouting. And you set the parameters. You know, it guides you through defining this project. So you might say, okay, I want to screen 3 columns. I want to look at pH, or I want to look at temperature. I want to try a couple different gradients, and I want to use these solvents. So then it will define how you examine these parameters, and it will generate the sequence for you. So it eliminates, you know, if you do 100 runs, let's say, imagine you have to define all of these different parameters 100 ways and not make a mistake. That's the biggest part. And I still make mistakes entering these methods and starting these sequences. So I think it's almost magical how it will generate this full sequence. It will tell you how much solvent will be consumed, how much waste will be generated. It will warn you if you're going outside the parameters of your columns. It will do automatic flushes. It's really cool. So if you want more information about that, just let us know. This is how you might evaluate some of that data that's generated from the software. You can see that you can define everything in the table based on the number of peaks so maybe you have a 10-peak mixture. Right away, just looking at this table, you go, well, I'm going to eliminate all the columns that only showed me 8 peaks or 5 peaks, and I'll look at the 9 and 10 peaks. You can absolutely manually review things, but the fun part is this new bubble plot, so you can look at things very visually. This is a great way to show other people data as well and say, okay, this column does this, and you can see it easily with a bubble plot. So lots of fun stuff with software. So getting back to how are we going to do this prep run on our analytical system, after we utilize all the tools, we get started, we've looked at our primer. Okay, so now I'm ready to go. What do I need to do? Well, if you're running an analytical prep run, more than likely you're using the same system. And more than likely you're using the same column or a very similar column. You may be scaling up from a very small column where you did your method development to a slightly larger, depending on what your goal is. You know, if you're only doing one injection of 50 micrograms or what have you, maybe you don't even need to scale up the column. But just to touch on these, you guys are going to have all these formulas. You want to make sure you appropriately scale things up based on a linear scale-up equation. What does that mean? That it means we'll have a predictable result if we scale up from our analytical run, even if we change the column size. So here's an example going from a 4.6 by 50 to a much larger than analytical column, but you can change this in your mind to something a little bit smaller, and just applying this gradient transfer formula. And all of the legend to this is here, but really all we're doing is taking the diameter, inner diameter of the column, the length of the column, and solving for maybe our new flow rate. And then we'll also use some other equations to solve for things like larger injection volumes. Or if you're actually changing systems, you want to make sure that you have things like the dwell volume calculated, because those can play into the elution time and how your peaks will resolve. So you want to make sure that everything is scaled up apples to apples. So here's our flow rate transfer equation, and then also looking at how much you can load on the column based only on changing the size of the column. if you change chemistries, all this stuff goes out the window, right? So you want to make sure you stay with the same chemistry. And it's really nice to also use the same particle size on your method development, your loading study, as you do on your final injections. So these equations are all here for you. What you'll find most people will do is use a calculator, which I'll show you a couple slide shots of that in a little bit. So this is just an example of how you might do this scale up. Once again, this column is probably out of the analytical range you guys are looking at, but this applies to all different sizes of columns, right? You might start with a 2.1 by 50 and move up to a 4.6 by 50. Whatever that is, if you apply these formulas that I had in the previous screen, what you'll see is your chromatogram will look nearly the same. Your retention time should come out very similar. You should have a predictable result so that no matter what peak you're looking for here, maybe it's the second peak, you know when to expect it to come out and that you should have the separation that you had in your method development, okay? So these formulas are extremely helpful. These are the success factors to make sure this works properly. As I mentioned, identical column chemistry is the most favorable thing. You want to have the same buffers. You don't want to make them very differently. You want to make sure if you do method development, you're using modifiers that you are using in your prep. If you're not going to use modifiers in prep, don't use modifiers in your analytical run. So try to keep everything as similar as possible. For those of you who want to use a calculator, it is much more simple. It's my preference. We have a great calculator at Agilent, but it's presently under construction. So this is an Excel-based calculator, which has a macro on it. So right now it's going through review as we update the features on it. All the formulas are the same. You can absolutely make your own calculator very simply. There's not a lot that you need to input for an analytical to analytical prep scale up. But what you can do also is go, I'm going to just move my little view box here. You can go to this website. This is a great website for a HPLC calculator. And there's lots of different features, even beyond prep, but you can do method transfer and calculate your output, very similar to what I'm going to show you. And this is the University of Geneva. So that's an online prep scale-up calculator that's very simple to use. But this is what you would do with our calculator, and it's very simple. This is why I like it, because all of our systems are in here. So the first thing you do is you enter your compound name. So mine is top secret mixture. You might say, oh, I need this much mass, or I need whatever it is, and this is where we start playing into that purification triangle, right? And then you could say, what is the abundance? So if my abundance is only 33% and I need 10 milligrams, it will spit out, okay, well, you're going to have a sample that's 30 milligrams in order to get this 10 milligrams. So whatever it is, it gives you a more realistic view of, oh, I may need to do 50 injections if I can only get the separation, if I can only load this much per injection. So you start to think about, well, maybe I should use a larger column, or maybe I should try to increasing my loading capacity on this column, and that's when your throughput becomes a little more evident. So we'll work our way through here. You look at the systems. Most analytical people are going from the one system to the same system. So I have the 1260 quat pump as our screening and our preparative run. So all of these conditions are the same, so that becomes very easy. And then we move on to the qualitative information. What's my analytical column? What's the size of it? What's the flow rate I'm using for my analytical analysis? So that way when it adds this to those formulas, it's all the same formulas I showed you on the other page. So now we're going to look at our method. So this is my analytical method. I just put a gradient method in here from 5% to 90% over 10 minutes, you know, whatever your method is. And then it's going to scale it for the new column. So here's my new column, a little bit larger, but still on the same system. So I use the example of going from the 4.6 to the 10. So I can actually inject quite a bit more on this column and flow faster. So it's even giving me a prediction of how many fractions I might collect on the system. It plugs in the column size and my analytical flow rate, chugs that into the formula and spits out my new flow rate. So it's very easy. So you see it's 4.73. And then in the next step, you see how all of this gets applied to the new gradient. So my new gradient is still about 10 minutes long, but we have a new flow rate. And then it even tells you how much mobile phase we're using so that we make sure to get this prepared. So you're going to use quite a bit more since we're going at 5 times the flow rate here. So these tools are very useful when you're doing scale up and you're trying to estimate how you can get the most out of your injection if you're doing more than one injection and you have the ability to do a little optimization. Column overloading becomes important because many people don't want to do just an analytical injection. Maybe your analytical injection is putting, you know, a fraction of a milligram or just micrograms on your column, and you need to process multiple milligrams. So why do one injection like this when you can actually overload your column and still get separation? So this can still be one injection, but maybe you can inject 10, 15, 20 times as much material and still collect everything. But understanding how peak shape is affected is very important. So as you see, we increase this injection volume substantially. Our peaks kind of move back, although the starting point is the same. But as you increase injection concentration, which if your injection volume is limited, but you need more on column, you may go with a higher concentration, and then we end up with this shark fin profile as you put more and more on the column. So understanding this helps you do this scale up. This is all for your reference. This is just another example of that. And you can see how column overloading, even though they look ugly, right? Analytical chemists see this and they shudder. But a prep chromatographer sees this and goes, that's what it's supposed to look like, because you want to get as much on that column as possible. Why have 1,000 fractions to deal with when you can have 4? That's what I say. Nobody wants to sit there and pull little test tubes all day or analyze them. So remembering our balance of purity, yield, and throughput, you want to make sure you make those goals and look at your loading as well. And you can see, just for your reference, you have many different parameters for loading, so you may need to go to a larger column to load up as much as possible. This is an example we did in our lab in Germany, and you can see a small loading study like this where we were able to put 3 times as much, 30 microliters. You know, if you're looking at one of these peaks, you're in trouble. But if you're looking at this peak, or maybe this peak, or even one of the last peaks, no problem. You could load this up probably 5 times even more, right? So understanding how this works can help you be more productive. Excuse me. Finally, I'll talk a little bit about an application that was done in Germany. That's where our Center of Excellence is, where they've developed all of our prep products. And they did exactly what we're talking about today. They did a scale up with a loading study on an analytical column on an analytical system. So here we see just a standard C18 on a standard analytical column. What we're going to do is take a look at this initial chromatogram where we injected 1 mg per mil sample. It's pretty typical concentration, right, for an analytical sample. And we did half a microliter of the sample. Low pressure, we've got lots of resolution here. So we could, you know, if we want to do 100 injections of this to get the amount needed, that's kind of laborious. If we could increase that volume to reduce the amount of injections, that's much better in this type of situation. So what they've done is a loading study, and as you can see here, this is the same sample increased to 15 milligrams of sample on this column. So this is a 75 microliter injection, right, versus what we did over here, which is a half a microliter injection. So if we can inject this much, think if you're getting paid by the amount of processed material, I would much rather do this in one injection and than do the previous, or having to pool, 100 fractions, or having to do this for 3 days versus doing it in 1 day. So this is a really good reason to look at improving your column capacity. And you can do a lot of this just with what you have on an analytical system. You can see we still had 94% recovery and greater than 99% purity because we had this great resolution between these peaks. So just in summary, it's very simple to go from an analytical HPLC to an analytical HPLC with PREP. You're just adding a fraction collector. It can communicate easily. The software will look almost identical. You just have some added functionality. It's extremely simple to do this automated delay volume calibration. And then your auto sampler will do the tray recognition, so will your fraction collector, Everything is still modular like you expect from Agilent, so you don't need additional software for this. Lots of tools to help you go through this, and lots of people to support you like Patrick and I as well. So as I mentioned, we have some references here for you. This primer is awesome. So if you want to learn a little more about PREP, I highly suggest you can get this from the internet. You can just Google this, or we can send it to you. You will receive this references page as part of the notes. So with that, thank you. I think I am pretty close to the end of the hour, but we have some time for questions, I believe. Is that correct?
Yes. Lori, thank you so much for that presentation. So just a reminder, everybody, if you have any questions, please go ahead and place them in the Q&A box located on your WebEx platform. I will be sending a recording out of today's presentation in the next day or two, so be on the lookout for that in your inbox. But I'll turn it back over to Patrick, who can go over some questions with you.
Yeah, so Lori, I don't know, excuse me, I don't know if you saw, but there was one question that I answered in the question and answer about delay volumes and the calibration, and how when you're moving from different flow rates on your system, is the delay calibration applicable to different flow rates? So I answered it with, depending on the range, you can, it will be applicable, but if you're in very drastically different ranges, you may want to do that a couple times. So I was hoping maybe you could give maybe you could give a little more insight into what those ranges might be and how specific you have to be for that.
Yeah, so the delay volume, for those of you who aren't familiar with that concept, the delay volume is really the mixing point to the head of the column, right? So unless you're changing tubing or adding components, that delay volume is not going to change unless you're going from one system to a different system, right? So if you're doing
sorry, Lori, interjecting. The actual delay volume wizard. Sorry, I was like, I didn't want to then ask it again, so I figured I'd just interject. So when you get that delay volume from the wizard, how applicable is it over a range of flow rates?
Thank you so much. So the wizard, which is housed in ChemStation. It's also available in OpenLab, and it's available in LabAdvisor. We'll walk you through calibrating this delay between, as I mentioned before, the detector that you're using to guide your fractions and the diverter valve at your fraction collector. So that's a static component that does not change over different flow rates. But if you're using UV, no matter what flow rate you use, that's stored as part of the firmware, and it will remain consistent. So if you are one day doing 1 mil a minute, it knows that that's a volume component. It's only when you add a mass spec, because the mass spec, due to different configurations, and the mass spec also, you have to make sure you have an adequate data rate to properly see your peaks as you have different flow rates. You have to calibrate it at the flow rates you will be using. So it is very simple to do. But most people, you know, especially on analytical, if you know you're going to be running 1 mil a minute and you're going to be running 7.7 mils a minute, you would do that calibration once at those flow rates, and that's the calibration you would use when you're using that flow rate on your column, and that's only for mass spec. So it's very simple. Does that answer that question okay? Excellent.
I think so, yeah.
Was there another question? Let's see. I think I saw something pop up. See it in the Q&A.
Yeah, you can. I think that'd be good for everyone to hear too. They were asking if adding a fraction collector, if I have an analytical system, can I just add a fraction collector? And I had said, yes, we just want to make sure that the firmware between older modules and newer modules will match and everything will work. But adding a fraction collector, basically, instead of the waste line, like Lori said at the beginning, going into a waste tube, where we're diverting some of that flow to collect the fractions from you in the collector, and the rest will go to waste. So it's pretty straightforward.
Absolutely. Simple. Just contact your account manager with whatever firmware, software, and modules you have, and we can verify all of that for you. Anyone waiting on the line? Yes.
I don't see anyone waiting on the line, but it looks like we are at our time. If anyone does have any other questions, please go ahead and you guys can place them in the Q&A box located there. I did want to go over.
Sorry.
Yes, go ahead.
I'm sorry. I wanted to make sure before we stop that people know that we have another webinar coming up that I will be doing using the prep calculator. And I believe it's in February. I don't know if it's on here. Is that me? I don't see it listed. But yeah, stay tuned for this or contact us and we'll send you the information. So I will be doing like a live example of using the HPLC scale-up calculator. But you can see there's also other events in the series. I'm so sorry I interrupted. Please continue.
No, you're good, Lori. Thank you. Thanks for mentioning that. We did have a question come through asking, does Agilent have any SFC capabilities with current fractionation units?
That's on my wish list for sure. So we do not have fraction collection for SFC at the moment. We do have analytical SFC, but we do not have the ability to collect fractions.
Thank you, Lori. All right, everyone. So it appears we have reached the conclusion of our event, so please join me in thanking Lori Sanford for a wonderful presentation. Thank you, Patrick, as well, for being on helping with our questions. So for the HPLC A to Z webinar series, these are the next 4 upcoming events. In regards to the webinar Lori was talking about, I can send you guys the link to check out and register for that one as well. But it's currently not listed in this slide currently. But for any webinars in this series, you guys can utilize this web address to look at all of our on-demand recordings and then also check out upcoming webinars and register for those. All right, so I will go ahead and leave the session open for a few minutes to receive any feedback or additional questions, but we are now going to close the audio line. Thank you all once again for attending, and on behalf of Agilent Technologies, we wish you all a great day.
Thank you.